Okay, today I'm going to talk about the scope of the problem of automated fact-checking in the state of the art. I need to admit that it is not possible to cover the extensive literature and the broad categories in this talk. So I've decided to first give a brief introduction, then explain the components of the pipeline of automated fact-checking systems, briefly give a list of fact-checking datasets, because datasets are central to the way the tasks are formulated. And then I arranged the rest of the talk based on three most popular datasets, Claim-Author, Clef, and Fever, because Claim-Author is actually when the story begins. And then for Clef and Fever, there are some shared tasks with interesting results, and it shows the trend of how the systems are developed and then matured in a few years. Okay, checking. There are two procedures in newsrooms for fact-checking. Internal fact-checking actually refers to the routines prior to publication to make sure there are not common errors in numbers, statistics, names, whatever, and ensure that whatever is going to be published is accurate. External fact-checking, which is a newer term, emerged in 2000, refers to publishing systematic assessments of truthfulness of the claims, particularly made by politicians and public figures in debates, speeches, and interviews. And this has given rise to many of those fact-checking outlets out there that you are quite aware of, like PolitiFact, FactCheck, and many more. There are three other terms that are associated with fact-checking: disinformation, misinformation, and fake news. So disinformation refers to any false or misleading information which is deliberately spread to deceive or mislead the public. Misinformation is the similar false information, but they say that it is unintentionally spread, and both of them are quite harmful to the public. So fake news can be considered as a typical example of online disinformation with different flavors like satire, fabrication, photo and video, manipulation, and others. What I'd like to note here is that the focus of this talk and my postdoc plan is not on fake news detection. And if you're concerned, so what's the difference between those algorithms for fake news detection and automated fact checking? All of them are mainly based on machine learning. But there are two primary categories when it comes to fake news detection. The network-based approaches that rely on interaction between people in social media, behavior analysis, they are completely different and distinct from automated fact-checking. But for content-based methods, which ground in analyzing text and content, linguistic features, and classification, of course, there is an overlap between fake news detection and automated fact-checking. I just wanted to mention the difference. All right, so what people are trying to do in order to automate the manual fact-checking procedure is to try to facilitate some of the tedious and components of the manual fact-checking which need human labor. So there are 7 different processes in a manual fact-checking procedure: getting familiar with the topic, identifying claims to be checked from a document, retrieving evidence, checking the sources, and then validating the claim, plus maybe later validating the whole reasoning change and checking for fallacies. So in automated fact-checking, these 3 components are going to be automated or facilitated by automated systems: claim detection, evidence retrieval, and claim validation. So although there is a little bit of confusion about, okay, what are the components in an automated fact-checking system, the pipeline has 3 basic subtasks: claim detection, evidence retrieval, and claim verification. Okay, the first one is usually a classification problem. The last one is also considered mostly as a classification problem because we're going to label claims. But for evidence retrieval, different methods like different information retrieval systems are used. Even for evidence retrieval, some people have been tackling the problem as a classification problem. So either one evidence is related to the topic or is useful for verifying the claim or not. A term which has been used in some of the studies is factual verification, and it refers to evidence retrieval and claim verification as a single task. Then in some systems, there is another component in between evidence retrieval and claim verification, which is called stance detection. So given a sentence from evidence and the claim sentence, the system decides the level of agreement or disagreement between those two. In recent years, it's been also some focuses on generating sort of explanation or justification. So when the system decides if a claim is supported or refuted by the evidence, people expect to see some justification. So in recent years, people have been trying to generate some sophisticated explanation and generation at the end of the pipeline. And then when it comes to evidence retrieval, of course, evidences are documents retrieved from Google searches or Wikipedia or other resources, but the whole document is not useful. So once the related document is retrieved, we need to select some passages or sentences, which we call rationale. So rationale selection is sort of, again, another classification problem. So data sets are important when we talk about claim detection and verification. So I categorize data sets into two parts. Data sets for claim detection, they include sentences manually annotated by human beings as checkworthy, not checkworthy, not a claim, or they are derived from some previously annotated data sets, some fact-checking data sets and others. And you can see here that most of those data sets are in English, unfortunately. So if you decide to implement an automated fact-checking system in another language, then the lack of data is your very first problem. Data sets for claim verification, some of them are quite small, so they're not very useful for huge learning models and deep learning models unless you use external data transfer learning. They are from different domains, extracted from Wikipedia or politics or fact-checking outlet website like SNOPS. And some of them are related to specific topic, for example, COVID-19. Some of them are huge data sets, some of them are not, but again, most of them are unfortunately in English. So for the rest of the talk, I will be focusing on claim author, CLEF, and fever. And the reason I picked these three data sets is, first of all, they are very popular. Secondly, it's not possible to cover all the work on automated fact-checking. And thirdly, the shared task related to CLEF and fever gives us a good point of view on how these methods are advanced just in a few years. Another thing that I'd like to mention is that I arranged this in a kind of chronological order. So I've started from 2015 and I go on until 2021, just focusing on the methods that people on those competitors in those shared tasks have been used and the way they've enhanced during the years. Okay, so 2015 is actually when the story of automated fact-checking began. So a team of researchers at the University of Texas in Arlington, they developed their algorithm. They haven't published the data set, but they developed this algorithm based on feature engineering, a simple feature selection method based on gene index of using trees, and some traditional classifying like naive Bayes and SVM and RF in order to automatically detect sentences from US presidential debates from 1960 to 2012 as non-factual statements, unimportant factual statements, and check-worthy factual statements. So the output could be represented to fact checkers out, okay, this is a claim, it deserves to be considered as a check-worthy one, so they can later on work on it. Then in 2016, they've started testing their algorithm in real time during the live coverage of 2016 US election. And they claim that, according to the feedback from fact checker, there is a positive correlation between the claims detected by the system as checkworthy and what fact checkers think need to be checked. Later on, in 2017, they expanded the features of Claim Buster. This time, again, the system is typically based on traditional machine learning and feature engineering methods, so there is no deep learning or pre-trained language model here. What they added is that in addition to the debates, they've also used some Parliament websites and Twitter to monitor the claims. And once the claim is spotted, they try to find out if that claim has been already fact-checked by referring to those repositories for fact-check outlets. If they find a match, then they show the user the report. If not, then they extract some keywords from the claim, generate some queries, and try to search the web to retrieve related evidence. So they also, it is like, I like to mention here that they call it the first ever end-to-end automated fact-checking system, but in a few years, things have changed drastically. Another effort to try to use Claim Buster in real world, in practice, was actually in 2018, when some people do tech and check cooperative through a 2-year project started sending automatically generated emails to journalists, and those emails were generated from the output of Claim Buster algorithm. So it was like every morning sent to some fact checkers from different news organizations. Okay, here are the claims to be checked. They were very excited at the beginning and they were happy that the system was working. But then they noticed that journalists started paying less attention to those emails because the system has been generating some noisy output, and many of the claims that the system deciding that are check-worthy, they weren't actually of any interest among that fact checkers. And finally, 2020, they released their benchmark data set, and it is just for check-worthiness. So it has more than 23,000 statements extracted from US general elections and annotated as with those 3 labels that I've already mentioned. So we can say that Claim Buster is a naturally generated data set. And we will go back to that because we have Fever, which is not naturally generated. Then we have this cross-language evaluation from Check That Lab, started in 2018 and still ongoing. So each year they release some data sets and they define some tasks and subtasks, and people participate trying the different models, and then they announce the leaderboard and they explain the methods. Actually, I'm not going to present any numbers right now, but you will see some numbers later for CLEF 2021, because in like 3 or 4 years ago, the numbers were quite disappointing. So the performance of the system, although they were trying to enhance them, they were far from being practical and useful. So the task for 2018 had 2 subtasks actually: to predict check-worthiness and to assess the veracity of the emails. It was both in English and Arabic, and it was the sentences and claims from debates and speeches from factcheck.org. So here you see the overview of the people participated in the shared task, and it gives us some sense of what methods were being used there. So the one in red is the winner. Christopher team, they've used recurrent neural networks. And as you see, they've used those typical feature engineering like bag of words, part of speech tags, verbal forms, negation, name entity. And they actually extracted those features, handcrafted features, and then traditional machine learning algorithms to check worthiness in English. Then for task 2, verification. Again, when you look at the learning models, of course, there is this LSTM occurring here and convolutional neural networks. But again, the winner, the Copenhagen team, as you see here, they've used convolutional neural networks and a traditional machine learning algorithm. And for the representation, you don't see any BERT or other new context-based word embeddings or those deep learning language model, neural network language model based. So you see bag of words and word embedding. And in addition to that, they also needed to find a function between claim and the document, so either similarity or access. So they are off-the-shelf similarity detection and measurement tools there. Okay, the reason I'm showing this is that the way the system changed in a few years is very, very important to understand how the problem was tackled before and now how people are seeing the problem now. The next year, in 2019, they updated task 2 by introducing a small data set of 69 claims, and they generated sort of annotations in order to re-rank the document. So the main focus of task 2 here was not just to verify the claim, but to measure the quality of the evidence retrieved from the web. And it turned out that those tasks specifically for re-ranking the pages and giving a label to the passages extracted from the text as usefulness label wasn't something very practical. It was challenging, and none of the competitors could actually beat the baseline based on Google search. So they found out that, okay, it's better to just rely on the way Google is ranking those web pages. So for task 1 in 2019, you see here that LSTM took the lead role, so long short-term memory. Using only word and syntactic dependencies, they won the competition. And still you see that most of the participants, they've been using these traditional machine learning and these had curated features of traditional language features, syntactic and other stuff. Okay, in 2020, they've changed the procedure. And again, there are English and Arabic data sets, but this time the inputs are not from the political debates, they are from Twitter. So the topics are different for English and Arabic. So AR and EN here stand for English and Arabic. And there are 1, 2, 3, and 4 components in the pipeline, plus that task 5, which is similar to the task 1 in the previous in the previous years. So this time they are going to label tweets as being check-worthy or not check-worthy, verifying them, and then working on retrieving supporting evidence and giving a label. So for task 1 Arabic, this is the methods and models, a summary of the best approaches. This is the leaderboard. They've used BERT, so BERT started emerging in 2020 in that Check That Lab. They had also by LSTM, by STI, there were some people trying to use traditional machine learning models and those traditional representations, but the one who won the challenge used BERT and with external data and machine translation. So it shows that even if you don't have some data set in one language, some automated machine translation can be used. So you can just translate your model to any other language. And it shows that it actually provides some evidence that machine translation can be helpful if your system is already developed in English and you want to convert it into another language. The same task on English, and this time Robert A transformer model 1. And still we will see some traditional models here, but they weren't really successful, although the second one is based on CNN, but the rest are not very successful. And by the way, for task 1 on English, unlike task 2, which covered different topics, it was just only a single topic on COVID-19. But you also see that when we move from Arabic to English, the BAT model, the previous one, is now the third one in the leaderboard. So it's not very unsuccessful still. Then for task 2 in English, in order to retrieve verified claims that are already being verified, again, we see that the winner here, both the AI team, they're using this Robert A transformer system. And there are a little bit of those traditional machine learning systems. So it started to fade away and people started to focus more and more on those transformers and pre-trained language models. In 2021, they've added more languages to the task. So here are the tasks they defined, task 1, 2, 3. For task 1, check-worthy estimation, they've used 5 languages, task 2, 2 languages, and for task 3, which I'm not going to cover here because it is related to fake news detection, it's not in the scope of my project. They, again, using Twitter and tweets, but in different languages, and they try to give them a label, like if it is supported or refuted by past verified claims. Okay, so I started to show you some numbers, so because they started to get a bit hopeful. Now they are far from being practical still. These numbers are the mean average precision. Okay, so we don't need to know the formulas of how these numbers are extracted for different languages, but the thing is, the larger the number is, the better. So we are trying to reach the 1, but we're still far from, very far from getting to that point. So I've just summarized the winners for different languages here, but I'm not going to go through all the details or all the numbers. But what we see here is that, again, in the leaderboard, the winners, they are using those RBAT or multilingual BAT models. So people started to just relying on those, and traditional machine learning algorithms have started to fade away. For task 1B, this time, check worthiness of debates and speeches. You see, again, those numbers are a little bit below when you compare them to the tweets. So one reason may be that extracting sentences from debates and speeches is a bit more challenging because there's a lot of, other sentences and other stuff out there. But again, the winner team has been used by Tweet, a very large language model trained on billions of tweets. For task 2A, and again, I'm not going to go through the details, but the winner, they again use RBAT and for Arabic, and for English, they use sentence BAT and some ranking using London. So, and the numbers are started to getting a bit better. So we can see the improvements made in a few years. Then for task 2B, which is detecting previously fact-checked claims. So the way they are actually formulating the problem is interesting. So it's not just always, okay, there is a document, you just try to find out which claims are check-worthy. They actually introduce that thing that if a claim has been already fact check, then it's better to go and find that instead of starting everything from scratch. So again, BERT, sentence BERT embedding is the one which improved the Elasticsearch baseline significantly, and it was the winner. It's still ongoing. So for 2022, they introduced 3 tasks: fighting COVID-19 epidemic, detecting previously fact-checked claims, which is now central to CLEF challenge, and fake news detection, which is out of the scope of this. And they've introduced more languages now. I'd like to mention here that when we review the methods using CLEF, we noticed that, as I mentioned before, it's not impossible to get quite significant results with implementing the system on one language and then using machine translation to use it in another language. So it's quite practical. Then we have the fever introduced in 2018. And the main difference between fever and the 2 previously mentioned data set is that these are not from political debates, and these are not naturally generated claims. So they ask human beings to start paraphrasing sentences from Wikipedia. So they're mutating them in different ways, and in some cases, the meaning even altered. And then again, they use human annotators to select evidence from Wikipedia. So it turns out that it's easier to get good numbers on fever when you compare it to other one. And it's natural because this is sort of fabricated, and the source for the evidence is just Wikipedia, which is the main source of the claims. And then they introduced the share task to label claims in a correct class. So say that if a claim is supported or refuted using the evidence from Wikipedia. And here are the numbers for fever share task. As you see, the winner team based on fever score, which is score mix of all the scores, is the one which selected sentences by sequence matching neural network, deep learning, and using a 3-way natural language inference engine with WordNet and element features. It was in 2018. So you can't expect everybody to use BERT and all that stuff. So you see still that for evidence, precision, and on the leaderboard, these ones. They use a combination of TF-IDF, which is a well-known and traditional method, and then string matching name entities and capitalized expressions. And then for the other one, for the recall on evidence retrieval, they just extract the non-phrases from the claim and use them to query the Wikipedia search API. These are quite sort of very traditional and, off-the-shelf methods nowadays, but back then they won the competition. And finally, last but not least, I'd like to also introduce 3 most recent works on fever. And the last one that you will see in a few minutes is actually my favorite one, the one that I like to also work on. Using knowledge graphs has attracted some attention in fact checking. This work, named as Knowledge Enhanced Fact Checking, is based on an external knowledge graph used to combine the knowledge with the retrieved evidence from Wikipedia. So given a claim, they retrieve some evidence from Wikipedia, some sentences. They also refer to an external knowledge graph and they select the related knowledge to the claim. And then in a very innovative way, they construct a graph which includes the claim and the knowledge from that external knowledge graph related to the claim and the knowledge related to the evidence extracted from Wikipedia. And then they feed this combined information into a pre-trained BERT encoder, and then graph attention, graph reasoning networks, and finally, they verify the claim. Actually, by applying this method on fever, they could improve the state of the art by more than 4% in terms of precision. So this is one of the recent works using knowledge graphs and combining them in order to enhance fact checking. The next one is related to generating explanation. There are many other papers, but I didn't want to go through all the details, but this one is very interesting because what they did again is they've been using both context, text, and knowledge graph at the same time. So they have this graph transformer encoder up here, and they have these recurrent neural network text encoder here. So they extract the context and they've got the fact and claim, and they extract the related knowledge from the knowledge graph. And then they train these two systems simultaneously. So at the same time, the system learns to classify the claim as refuted or supported using the contents and the evidence and the knowledge graph at the same time, because they're combining them through these attention layers. And they also learn to generate some explanation. So in most of the systems, fact-checking, automated fact-checking systems that we've been talking about, explanation or justification is nothing but those rationale sentences from evidence documents. So they haven't generated anything specific. But this one has addressed the problem in a different way. So they've used this decoder with copy mechanism. So it uses some parts of the claim in addition to the knowledge from the knowledge graph and the context in order to generate explanation. The thing is, when you design such a system, then you need some human annotators to say how good the explanation you generate, the system is generated is. So it is a little bit challenging. It needs some annotators and some extra work, but they've shown that this system produces quite good explanations for the verdict of the claim. And this is my favorite work, actually. And the reason I like this one is they tackle the problem in a completely different way. So by far, you've seen that, okay, whether you're using traditional machine learning and curated feature, or you're using those deep learning and transformers or pre-trained language models, you are looking at the problem mainly as a classification problem. But what if we look at it as an evidence-based factual error correction? So we have a claim, and we know that that claim could be a sort of corrupted factual statement. So why not trying to correct those corrupted parts? I'd like to mention here that the results they got in this paper are not very promising. So, and it's actually natural, we can expect that, because first of all, we don't have a good data set that helps us building our models. We don't have a factual error correction data set. Plus, if you want to correct the claim, the way you are masking the words and terms in the claim is important. So if you know which part of the claim are questionable, which parts of the claim are critical to make it true or false, then you can mask them directly and teach the system to replace them with the correct one. But since we don't have that luxury right now, they've decided to use different type of masking methods. So they mask the claim. So if it is the given claim, and we don't know if it is true or false, but we know that it can be corrected. So they either randomly mask some of the terms in the claim, or they use some heuristics. And then they train this corrector, so it gives us the corrected version of the claim. You at the end that, okay, masking is very central. So if we can find a method to identify those critical terms in claim, then designing a factual error correction system would be much easier. It was all, I guess it took